When a wastewater treatment plant treats 1 liter of wastewater, it does not only produce clean water. It also produces something that we see very little, but which plays an essential role in the entire process: sludge. Long considered a simple residue, sludge is in fact a very concentrated material. It contains organic elements, minerals, microorganisms, and sometimes even an interesting energy potential. In other words, it is not an insignificant remainder, it is the concentrate of everything the water was carrying. And this is where the topic becomes central to water engineering. What do we do with this material? How can it be stabilized, transformed, or valorized without creating new pollution? The boundary between waste and resource is much thinner than we imagine. Wastewater sludge consists of the solid residues produced throughout the treatment of wastewater. From the moment water enters the treatment plant, part of the material it carries begins to separate. This is the origin of the first sludge. During sedimentation, the heaviest particles naturally settle at the bottom. These are called primary sludge. They are made up of suspended solids, sand, settled fats, and organic particles. Then comes biological treatment. Microorganisms consume the dissolved pollution in the water. As they grow and then die, they form a second category, secondary sludge, which is richer in bacterial cells and transformed organic matter. In most treatment plants, primary and secondary sludge are mixed to form what is known as mixed sludge.
So sludge is not just dirt. It is everything the water was carrying, concentrated in one place.
Exactly, and this concentration is significant. Sludge contains between 70 and 95% water. The rest consists of organic matter, minerals, living or dead microorganisms, and sometimes small traces of heavy metals or micropollutants. Once produced, sludge must be treated to become more stable, less wet, and easier to manage. The first step is thickening. This consists of increasing the concentration of dry matter by removing part of the free water contained in the sludge. This step can be carried out by simple sedimentation or using equipment such as gravity tables or flotation units. Thanks to thickening, the dry solids content often increases from 1% to around 6 or 8%. The less water there is, the more efficient the rest of the treatment becomes. Next comes stabilization. The objective is to reduce the biological activity responsible for odors and fermentation. Two main processes exist. The first is aerobic stabilization. Air is supplied, microorganisms rapidly consume the material and produce heat. The second is anaerobic stabilization. This process takes place in the absence of oxygen, inside closed digesters. The degradation is slower, but it produces biogas, a mixture rich in methane. This biogas can be used to produce heat or electricity. In some modern treatment plants, the energy generated by digestion covers a large part of internal needs, reducing the consumption of fossil energy. After stabilization, the sludge is dewatered. This step aims to remove the water still trapped within the structure of the sludge. Centrifuges, filter presses, or drying beds are used for this purpose. The dry solids content can then reach 20 to 30%, which greatly facilitates storage and transport.
At this stage, the material obtained is compact and much easier to handle.
Depending on the final destination of the sludge, hygienization may be required. This step eliminates remaining pathogenic germs. It can be achieved by heating, by adding lime, or through extended composting. Thermal or solar drying can then raise the dry solids content to more than 80%, or even 90%. The result is an almost completely dry sludge. Throughout the process, several technical parameters play an essential role. Dry solids content, which determines the amount of dry matter. The retention time in digesters, often between 15 and 30 days. And the operating temperature, generally around 35 to 38 degrees Celsius for mesophilic digestion. Once thickened, stabilized, and dewatered, sludge is ready for its final destination. Depending on its quality and composition, it may enrich soils, produce energy, or be eliminated when it is too contaminated. Once treated, sludge becomes a more stable, drier, and safer material. This raises an essential question: what can be done with it? Three main pathways exist today: agricultural valorization, energy recovery, and, as a last resort, disposal. The first pathway is agricultural spreading. Stabilized sludge contains nitrogen, phosphorus, and a significant amount of organic matter. These elements are valuable for improving soil fertility and reducing the use of chemical fertilizers. Before being used, sludge is analyzed to ensure it meets sanitary and environmental standards. When these conditions are met, it can be composted, hygienized, and then applied to the soil as an organic amendment. The second pathway is energy recovery. Digested sludge produces biogas, a mixture rich in methane. This gas can power generators to produce electricity, heat, or even be purified into biomethane for injection into the gas network. Some treatment plants reach a very high level of energy autonomy through this pathway, significantly reducing their carbon footprint. After drying, sludge can also be used as fuel in suitable facilities such as cement plants. In this case, its calorific value is recovered, and the ash resulting from combustion can sometimes be reused to extract mineral elements such as phosphorus. The third pathway is disposal. When sludge contains too many heavy metals or micropollutants, or does not meet the criteria for agricultural spreading or energy recovery, it must be incinerated or sent to a specialized facility. This solution is necessary in some cases, but it is considered a last resort because it does not allow the recovery of nutrients or organic matter.
In reality, sludge is neither entirely waste nor entirely a resource. It is a complex material whose potential depends on technical control and environmental choices. This nuance is what makes sludge management a major challenge in water engineering. It now remains to bring all these elements together to understand what wastewater sludge truly represents today, and what it could become tomorrow.
And now, grab a glass of water, and stay hydrated. If you're into this topic, don't forget to subscribe, hit the bell, and come with us to explore the world of water.